So the site page today is going to be water. Water. You guys know how to do this one? Go to brianteaches.com, go to chemistry, scroll down to water. Now, I think at this point we've done enough of these that I can tell you that everything on the white background is material you have to copy, and everything in the blue background is original content that we're going to work on. If you can't already tell, the white background material is actually getting a lot longer because there's more stuff to cover. And I have a lot of fun making these. It covers all of the things that I've learned in chemistry and biochemistry, and hopefully at some point in time you guys might get questions like this for your classes and you'll have an idea of what they're talking about. So, best way to start this, open up your site. Go to sites.google.com. Open up your site. Open up period 2 for you guys, or whatever period you're on. Pages. Make a new page. Call it water. You got to put a button to that page on your home page. So let's make a copy of the cesium page, or the cesium button. Let's edit this so it says water, and it links to the page for water. And pick an image for your background. Let's just do image. Let's do select image. Search. Let's look for what they got for water. Sure, I think I use this one for the button, and then I use the other one for the background. So then go to your water page. Maybe you want to change that. I think that I just used this one. And we're going to move one set over here, one set over there. We're going to copy over all the information from water. Probably make it smaller. Control minus 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 will make everything smaller. And then you can copy over everything. Picture, text, picture, picture, text, 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 picture. You guys know what to do from there. Okay, let me cover what water is all about and why I think water is important. You guys probably know a lot about water, but hopefully you learn a little bit more. Okay, so H2O makes Earth special. 71% of Earth's surface is covered in water, and 96% of its water is found in the oceans. That means most of our water is salt water. It means it's not potable. We can't drink it yet. Without water, Earth would likely be another boring rock in the sky. What's so special about water? Well, first off, water is the standard polar solvent. Polarity. When I say the word polar, what do you guys think of? Polar bears. That's usually what people think of first. Why are they called polar bears? Why are they called polar bears? Where do they come from? North Pole. That's why they're called polar bears. Polar bears are crazy. Have you guys ever seen videos of polar bears? They're not really cute. No, they're murder machines. Like, there's documentaries on people who take photographs of polar bears. They say that if you see a polar bear, you're already dead. I can't show you a video that's that gnarly, but they're pretty murderous. I should have pulled up a video of that. I'm going to pull one up. I'm going to find one. I'm going to link it here so you can see it. We'll go over it tomorrow. But anyways, these guys, I said because of that, they're bipolar. Do you guys know what bipolar is? Okay, what's bipolar? Sure, yeah, two different, right? Alternating. Some people who have bipolar disorder, they might be very manic and they might be very depressed. They go through these ups and downs, just like polarity our north and south pole. They're opposite ends. Oh, and just as an FYI, do you guys know what a meter is? Like the definition of a meter? You could. It's right there though, Melissa, if you just look. It's right there on the page. It says. What's it say here? You, 1/10,000,000th of the distance between the North and the South Pole. So when people started measuring things, they have to have some sort of reference point. What the heck is a meter? What is a meter? We know what a meter, like we have yardsticks, right? We have meter sticks. You can say, oh, a meter is that. But where did they get that measurement? That's where they got the measurement. They determined the amount of distance between the North and South Pole, and they said 1/10,000,000th of this is what we will call a meter. And that's what a meter is. Kind of a weird standard, but it is what it is. Water is the standard polar solvent. This solvent is the thing that dissolves things. Polarity is the state of having two opposite or contradictory. I can't even say that right. Tendencies, opinions, or aspects. In chemistry, polar molecules have one end that is positively charged and one end that is negatively charged. So polar substances have a positively charged end and a negatively charged end. Just like the North and South Pole are on different ends, bipolar emotions are on different ends. Polar molecules have a positive and a negative spot. So that's actually defined by something called electronegativity. The electronegativity of elements has been charted, and here's a graph on this. I will quiz you on this at some point in the future on electronegativity. That's going to be something that we deal in Unit 3. The most electronegative elements are the ones in the top right. Oxygen is pretty electronegative. That means it loves electrons. It's going to steal electrons. Oxygen will do that to almost anything, and when it steals electrons, it's called oxidation. So if you guys have ever heard of the process of oxidation, it's just when something loses electrons because oxygen is stealing it, or some other element. And that's what causes most of our aging, is oxidation. That's what ends up killing us, is long-term oxidation. Anyways, because of their specific electron and proton configurations, each element has an electronegativity and electron affinity. This indicates how strongly those elements pull on electrons. When electrons are shared between atoms in a molecule, the more electronegative element pulls on those electrons and creates an uneven distribution of charge. This creates the polarity that water is famous for. So oxygen wants electrons more than hydrogen. It's negative. This is negative, this is positive. That becomes polar, and it dissolves other polar things. It is the standard polar solvent. It's a thing that we dissolve almost everything in that's polar. As a polar solvent, water separates other polar and charged substances like NaCl. NaCl is salt. When we pour salt into water, what happens to that? Well, the positives and the negatives that once were together, these guys used to be together in a grid. They get pulled apart by the positives and negatives on the water, and they get surrounded, and that's how things dissolve. And as far as we know it, life requires a polar solvent. Our blood is 90% water and helps transport polar salts, minerals, and proteins. I don't know if there are any life forms that can exist without blood. We have a lymph system as well, and that's where all of the non-polar things are moving in our body. But I think that most life forms develop a circulatory system before a lymph system. Okay, why? How does water work? Because I asked you guys why. Why? Well, most of it can break down to hydrogen bonding. Hydrogen bonding is responsible for a lot of water's unique properties. So we just talked about how oxygen loves electrons. It pulls on electrons harder than hydrogen. So it has more electrons here. When oxygen pulls electrons from hydrogen, it creates partial positive and partial negative poles. These partial poles are represented by the Greek lowercase letter delta. This is delta as a lowercase. instead of the triangle. That's the uppercase one. The delta positive, this partial positive from hydrogen in one molecule, will react with a partial negative from oxygen in another water molecule. The negative oxygen reacts with a positive hydrogen from a different one. We call this a hydrogen bond. When the hydrogen of one water molecule interacts with a negative pole of another molecule, and it's got to be one that includes oxygen, nitrogen, maybe fluorine. That's where you're going to get a hydrogen bond. And hydrogen bonds are super important for life. Most of the unique and significant properties of water, including many of its life-sustaining properties, can be attributed to hydrogen bonding. Okay, so I asked you guys in the quick write, which one is more dense? Solids. Solids, 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 solids. Everybody seems to say solids are the most dense. I agree with that. I agree with that. For buoyant force, most people are saying it sinks. A more dense object will sink. Okay, fine. If solids are more dense and dense things sink, which one will float on the other? Will liquid water float on solid water, or will solid water float on liquid water? Does ice float? Why? Isn't it solid water? Why? Because it's water. That's actually a good explanation, Ileana. It is actually, because you guys should have been thinking, wait a second, solids are more dense. More dense things sink. Why the heck does water in a solid form float? Shouldn't it be more dense? If it's a solid, shouldn't it be more dense? Shouldn't it sink? You think so, but not ice. Ice is really abnormal. It's actually not the norm. For most substances, the density of solid is greater than the density of liquid, which is greater than the density of gas. Why does solid water float on liquid water? Hydrogen bonding. That's the reason. So here's the density of ice. The density of ice is actually less than the density of water. It's a weird substance. Not every substance does this. Not many substances do this. A few do. It's because of these partial or these hydrogen bonds. These hydrogen bonds lock these guys into place so that they have to orient themselves in this particular pattern. It's not as dense. It's a weird substance. So the fact that ice floats should weird everybody out. But we've seen it our whole lives, so we don't really think about it too much. But it's weird. Why? Why does it do that? Hydrogen bonding. Now you can say, hydrogen bonding. Hydrogen bonding can only occur at specific angles. When water freezes, it locks molecules into a specific shape that is actually less dense than liquid water. This abnormal property allows ice to float. Steam is like not dense at all. It spreads out like crazy. The density of water is actually the basis for the metric gram, the standard for measurement. If I just asked you guys what a meter was, now you can say, oh, the meter is 1/10,000,000th of the distance from the North Pole to the South Pole. Is that worthless trivia? Probably. But the density of water is where we got the gram. So when scientists measure mass, they often use the gram as their reference unit for measuring mass. You guys have been using the scales. You see the gram. What the heck is a gram? How do we define a gram? What is that? Originally, the gram was based on the mass of 1 cubic centimeter of water. Does anybody know the abbreviation for 1 cubic centimeter? What would you abbreviate that to? Cubic centimeter. If you had to abbreviate that. I would say maybe cc. Have you guys ever seen any like medical shows where they say, this person needs 50 cc's of this medicine? That's what that is, cubic centimeter. So the mass of 1 cubic centimeter of water at 4 degrees Celsius is the gram. Water is so important to our species that we compare all of the masses to that. Do you guys know the prefixes? Are you guys comfortable with the prefixes? Like you have a gram. If you have 1,000 grams, you would have a kilogram. If you had 1/1000th of a gram, you have a milligram. Hopefully you guys are comfortable with that because I'm going to make you put together a chart. And that should be easy, hopefully. But anyways, 1 gram is 1,000 milligrams. It's also 1/1000th of a kilo. So you go from grams to deci to centi to milli, and on the flip side you go deca, hecto, kilo. Anybody know what's above kilo? I guess we'll find out when we get to the graph. Okay, water has a relatively high boiling point and is the standard for the Celsius scale. I've asked this a bunch to students when they are working with water. It takes a long time for the water to heat up, right? In all of our labs, it's been taking a good amount of time to heat up water. That's because of those properties of water, because of the hydrogen bonding. So water is actually the standard for the Celsius scale. What does water boil at now? You guys should know this by now. 100 degrees Celsius. Water boils at 100 degrees Celsius. It freezes at 0. That's where we got the scale for Celsius. It is the standard. So it takes a lot of energy to break the hydrogen bonds that keep water molecules together. Because of these hydrogen bonds, water exists as a liquid for a large range of temperatures. This prevents our blood from boiling or freezing, even with large variations in air temperature. That's actually pretty important that it has a large specific heat, because there are some substances that if you give them a little bit of energy, they go up in heat a lot. Like if we were made of metal, then our blood would shoot up in temperature if we went outside. But because it's mostly water, and we're made of mostly water, we can resist changes in temperature pretty well, to an extent. So water has an abnormally hot, that's called specific heat, and we'll also be talking about specific heat very extensively in a few weeks. Water has an abnormally high specific heat, allowing it to absorb more thermal energy without a significant rise in temperature. Beaches are always cooler, almost always. They're cooler than inland areas. We're sort of inland, we're in a valley. If you went to the beach or you get closer to the beach, it's just going to be cooler. Why? Well, it's because of that specific heat. So water can absorb a lot of energy before it goes up in temperature, before it wiggles around, because the wiggling is what's temperature, is the kinetic energy. But because it has so much energy built up into these hydrogen bonds, it takes a lot of energy to break these first before they start to wiggle and heat up. So that hydrogen bonding means that it has a really high specific heat. It takes a lot of energy to warm it up. The specific heat of water has a pretty interesting unit. The specific heat of water is 1 calorie. Do you guys know what a calorie is? Right? It's something that you eat, correct? Well, what is that definition of a calorie? It's the amount of energy needed to raise 1 gram of water by 1 degree Celsius. What's up, Patrick? Yes, I'll look at it. I will go over all of the grades. I'll start looking at them tomorrow. But everything will go in before the 10-week. Unless you specifically request it for other purposes. So a calorie, we'll also be doing stuff on calories. The calorie is also based off of water. It's the amount of energy needed to raise 1 gram of water by 1 degree Celsius. Its high specific heat and unusual density allowed aquatic life to thrive. So why is water important to life? Why do we need water? Besides the fact that it's polar solvent and it has a really high specific heat so that our blood doesn't boil in small variations in temperature, it also, because of that, the way that the density works, when you have a body of water that's frozen, and our whole planet has gone through these periods of time where the whole planet freezes over. Well, if water froze from the bottom up, then everything would freeze, and all of the life forms in those prebiotic pools of water, Those would have all died. So, because ice floats, it makes this layer at top that actually insulates from other cold and keeps all of the fish and all of the aquatic wildlife living. So because of that weird property of water, because of those hydrogen bonds that keep it floating, that keep ice floating, we were able to have prebiotic life. And our ancestors came from that. I mean, this is one of our ancestors, guys. Let's see if it pulls up the picture. This is one of our aunts or uncles. Come on now. Right there. Yeah, that's where we came from. At some point. At some point, that's like your great 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 grandma or something like that. I think she's beautiful. Don't you guys think so? Yeah. I think that this had wrists. I mean, we had to develop wrists from fins. They had fins. They had to start using wrists. They had to develop air systems. But anyways, that's that. That's one big reason why water is important. And I remember very specifically an exam in biochemistry where they asked about these things. Why is water important to life? And you had to list off all of these things. Otherwise, you didn't get credit. So hydrogen bonding gives water cohesive and adhesive properties. They are different. Cohesive, co is like with, so water sticks to other water. Adhesion, it sticks to other things that aren't water. Because of that, water has been able to be used by plants to pull water up those long trunks and feed the rest of the plant, give it its sufficient water that is necessary for all the chemical processes that occur. Cohesion is what gives you those distinct drops. But adhesion actually keeps it stuck there. This is something that's usually joked about. Have you guys ever seen this dihydrogen monoxide warning? With cyanide, I asked you guys if water was fatal. Can water be fatal? Yeah, I can. You can drink too much. You can asphyxiate. So there's always this joke that chemistry teachers will make about warnings about dihydrogen monoxide. Dihydrogen monoxide, inhalation, even in small quantities, can cause death. Prolonged contact with its solid form results in severe tissue damage, aka don't hold ice for too long. May cause diaphoresis, micturition, and acute tissue hydration. Yeah, water's not dangerous. Well, it could be. It always could be, but not if you're smart about it. But we don't have that much fresh water, actually, on this planet. It's kind of scary. And it might be one of those things that we're really going to have to be fighting for in the future. Our water usage is going up as it gets hotter, and the costs are going up too. There's people who joke about a post-apocalyptic life where people are freaking out about water. Did you guys ever see the movie Mad Max or the sequel? It's basically based off of this sort of thing, that we're going to run out of fresh water. Could happen. It could happen. We got to be kind of cognizant of how much water we're using. So, this is how much water we have on the planet. If you pull up this is our planet. If all of the water was pooled together, it would make this little drop here, because our oceans are really not as deep as we think they are. And then all of the fresh water is this little drop right here. All the fresh water in the entire planet. It's actually not that much. Dihydrogen monoxide warnings might falsely give the public the impression that water is dangerous. Jokes aside, our access to potable water is water you can drink, is dwindling and may prove to be a massive socioeconomic issue in the future. Global climate change has shifted weather patterns and made some areas more dry, while others are flooding, like New Orleans, Miami, and New York City are flooding all the time while we're dealing with droughts. That's messed up. It's not helping. Water is the standard for life, and we need to treasure it. Okay, so if you guys copy all of that white background material, then that should be good. I'm going to make the video right here, but here are the things you guys need to do. Because water is the standard for all of these measurement systems, water is the standard for, well, it's the polar standard. It's also the standard for the gram, the Celsius scale, the calorie. Because it is the standard for all of those, there's a lot of units. I need to talk more about units. So you guys are going to have to know the units. So what I want you guys to do for the original content, and I have you guys for, oh, I can go over probably all of it. Yeah, I can go over all of this. So first thing, scale of the universe. You guys ever use scale of the universe? Go to scale of the universe. Google scale of the universe. Go to the second one, not the first one. The first one doesn't work on HTML5 anymore. So we load this up. Oh man. This is giving me a problem before too. There we go. Okay. Scale of the universe. This, I'm going to turn up the volume. Do you guys know how large and how small our universe really gets? It gets ridiculously small and ridiculously large. So if we have a little shrew right here, or a chicken egg, we get smaller. So the chicken egg is about a square inch. And we go further down, pencil lead, an ant, a grain of sand. That's an LCD pixel that we are looking at. We just keep going down until we get to infrared wavelengths. A skin cell is actually pretty big. That's really big. The nucleus, an X chromosome, that should be in the nucleus. You can keep going down. Bacteriophages are viruses that attack bacteria. Here's ultraviolet light. Look how much smaller ultraviolet is compared to red light. It's so much smaller. It does so much more damage. You can keep going down and down and down. Here's an atom. We're just getting smaller. It's so microscopic. This you can't really see. So what I want you guys to do is, if you can see, people speculate. Maybe you've heard that there are protons and neutrons that make up the atom, but we've gone further than that, and we've actually said that there are fundamental particles that constitute a proton or a neutron, like down and up quarks, and there are even more particles. And if you keep going further and further down, and further and further down, and further and further down, eventually they say that everything is a string, and we're all basically just vibrating strings. All energy and mass are just vibrating strings. We're all just a bunch of strings. That's it. Strings. That's what string theory says, that we're all just like we're just a big old pot of spaghetti vibrating at specific wavelengths. And those strings vibrate at some frequency that altogether makes up some sort of pattern of energy or matter, or energy, and then the energy makes matter. Anyways, that's really complex stuff that I don't know enough about, so I'm not going to speculate on it too much. If you go to JPL or hang out with a scientist in NASA, they can maybe talk to you guys about that stuff. That's how small our universe gets. Our universe also gets super big, super massive. When you look at things from a really small scale, we seem really impressive and grandiose. Like, life seems super impressive when you look at the very, very, very tiny scale. I feel like when I look at the big scale, and this is why I'm not crazy about space science, it makes me feel completely insignificant. Like, oh cool, I'm made of so many, just trillions of strings. That's impressive. But then when you pull out, you're like, oh, but I'm a speck of dust in the universe. Because it just gets massive. Like, look at how tiny the Earth is now. The Earth is is less than a pixel. It's so itty bitty, and there's things that are just, they scale up to be so massive. I don't like looking at things in space. It gives me an existential crisis. Like, what's the point of living when we are so tiny in comparison to this stuff? Anyways, what I want you guys to do is find 4 objects that you are going to take a snip of on the scale of the universe. So I picked a bottom quark, an X chromosome, Halley's Comet, and Omega Centauri. And they're kind of spread out. What I also want you guys to do is make this prefix chart. So how the heck are you going to make this prefix chart? I actually didn't give you the option to copy this because it's not a Google Sheet. I embedded this as an iframe, and I want you guys to do the same thing. An iframe is just a different way to embed it, and I'll show you how to do that. But make a prefix chart. So go to sites.google.com, or not sites, go to sheets. Make a new prefix chart. Let's make the first one prefix. And here's the best way to do this. I haven't made it easy enough for you to copy that you can just copy the Google Sheet. Instead, you're going to have to do it the manual way. You're going to have to mouse over all of this and copy that. And let's see what it looks like if I paste it in. It's not too bad, but you might have to do some fixing of it, like delete mine. Let's delete this column and see what happens. That's fine. I want you to merge them and make this the new prefixes. Okay, so these are the prefixes. Some of these prefixes you guys might be familiar with, especially if you do anything with technology. So if you multiply something to the 10th power, it's a deca. Then multiply that to the 2nd power. If you bring it to 10 to the 2nd, that's a hecto. Then it's a kilo. After a kilo, like if you had data, kilobytes. What's 1,000 kilobytes? Do you guys know what? You guys know what's above 1,000 kilobytes? You get a megabyte. If you have 1,000 megabytes, you have a gigabyte. If you have 1,000 gigabytes, you have a terabyte. If you had 1,000 terabytes, you have a petabyte. It keeps going up and up and up and up. A Google, just so you guys know, the name for Google was actually a misspelling of a theoretical number that somebody made called a Google, which is 10 to the 100th power. So when the creators of Google were making their name, they thought that that was kind of interesting, that 10 to the 100th is basically more numbers than we would ever need in the universe. These are some of the names. It's expected that you guys are somewhat familiar with these prefixes. Especially when you get to college, they're going to assume that you know that 10 to the 3 is kilo, that 10 to the 6 is mega, 10 to the 9 is giga, 10 to the 12 is tera. I think that's just mostly because of technology. Should give you a good way to see that. I'll close that. And then the flip side, deci, centi, milli, centi. There are 100 centis in a single thing. Like there are 100 cents in a dollar. There are 100 per cents, cent. A century is 100. So centi is 1/100th of something. Then milli. 10 to the negative 6 is micro. It has this little symbol called mu. Then nano, pico. That's usually where people stop. Some of these ones are still in proposal. The ronto and the quecto are being discussed. So what I need you guys to do is make this copy of this chart, and you're going to also include the scale of the items that were in your scale of the universe that you picked. So it should tell you, oh, the bottom quark is at 3 times 10 to the negative 23. So I put it over there at 10 to the negative 21 is the scale there. X chromosome is micrometers. Micro is right here, is the millionth. 10 to the negative 6. Halley's Comet is 10 to the 4. Then you will also have to be responsible for making this chart for units. The things that you need to do here in order to get your points, in addition to actually creating this table with all the data, and you could copy it just by copying it like this. You can't do the full copy with Google Drive or Google Sheets because I embedded it as an iframe, and I'll show you how to do that. But you can copy all of this. The things that you need in here in order to get full points. The headers. So here I'll show you. I still have you guys for another 12 minutes. I can get through all of this. Okay. Let's copy this. Here's our water measurements. Let's make another one called units. Oof. Oof. That is not copying very nice. Let's see if I can get a better copy. If not, you guys might have to just copy it manually. But some of the things that I want you to do manually, if that is the case, let's see if I can make it smaller. Let's see. Let's copy that. Maybe that'll work. Okay, that works. You guys should always do that so that it wraps. It should be middled. It should be centered. And for this one, I'm getting more particular. I want to make sure that you guys are mastering all of the tiny little skills involved with this, including coloring the header cells. You can do that by using the paint fill. You can use whatever color you want, but I want those to be filled. I also want you guys to use the borders correctly. So use cell outlines as appropriate. The cell outline tool, when you make this, is this right here, the borders. I want you to change the color for the borders to be something appropriate, and you're going to change all of the borders so that it matches this chart. I also want you to use the clip art. It's easier to shrink it. I want you guys to use that clip art right here. There's two ways you can do that. You can either embed it straight into the cell. Like let's say I grab this this first one. So I could copy the image address. Maybe that'll work. Let's go insert, image, image in cell. Let's go by URL. Let's see if that works. That doesn't work. So instead what we'll do is we'll have to download it. So go ahead and save the image. Save it at, ooh. Copy, save image as is an HTML document. That's not right. Copy image address. Let's see if this works. Oh, wow. Is anybody able to download this image? You know what? You can search Google for the image. Maybe that'll work. No. I'll see if I can get a better way to grab these images. You could screenshot it, but that's not what I'm trying to do. I'm trying to get you guys to embed the clip art in here, and I did supply this clip art, but it should be easier to download it. The saving image is saving it as a HTML file, which is not what I want. And copying the image address isn't working either. So I'll find a way to give you guys the folder so that you can have this clip art. But once you find that clip art, like let's look for, I'll find one. You can use whatever clip art you want, but let's say I just Googled ruler clip art, copy the image address. Maybe this one will work. And that works, and I can insert the image. And it does that. Now we got to change it because it's filling out the image. And we'll fill in as appropriate. That's clip art that's not really working that well because it's not transparent. That's not what I want. But I want you guys to copy that chart. So this is basically a way to test your copying skills and your chart making skills in Excel. Play around with some of the qualities. Merging the cells, you should also be able to use this when I have you do a customary abbreviation like this, or the customary in abbreviation. These are all merged. All of these cells are merged. And I want you guys to practice that. So if I had 3 cells that are merged together, you merge it. And then if you wanted to have a new line for each of these, you have to hit Control and Enter in order to get a new line. And they will always be on a new line if you hit Control and Enter. So those are some just small little details about sheets that I want you guys to pick up. The last thing I want you to do is to create a new measurement scale that's based off of your cells. So a meter is 1/10,000,000th of the distance between the North and South Pole. Why did we pick that? I don't know. It's just what they picked. But I want you guys to make a new measurement scale based off of your height. So what you're going to do is pull out, you're going to have to get your height. I had a ruler. Here's a ruler. I did 3 measurements. I did a measurement for my height, for my wingspan, and then for the measurement from palm to fingertip. So for those, I got height was 73 inches. My wingspan was 79. Does anybody want to have their height and wingspan measured? Is anybody brave enough for it? Okay, let's have somebody. Yeah. April, you want to measure his height and wingspan? Measure it. Measure his height and wingspan. Well, how do you measure height? Got to stand up tall as possible. Do most people have a longer wingspan than their height? I'm not sure. I'm actually not sure what the data is. Huh? 70. Now what's his wingspan? Wingspan, tip to tip, fingertip to fingertip. There you go. Yeah, as wide as possible. Yeah, there you go. Uh-oh, actually you probably need somebody else for that one. Bonnet, you want to help him? Hold his... What's the wingspan? So his wingspan is less than his height. Most people, I think, are actually, they have a smaller wingspan. If you have a larger wingspan than your height, you're like a basketball player or a volleyball player or a swimmer. Does he play basketball? But if you had a higher wingspan, now my height is only 6'1", but they were doing my wingspan the other day. It was 79. So that's my wingspan is like this. So what you're going to do is you're going to find out what your height is, and you're going to make that your personal unit. That's one of you. All of the other units are going to be based off of that personal scale. You're just going to divide it by that number, that point, whatever value you get. That'll give you 3 points. The last thing that you need to do as a potential, this is extra credit. Do you guys know how much water you use on a monthly basis? No? Most people have no idea how much water they use. My cousin the other day asked me if he uses too much. His water bill was $1,400. He used 1,900 gallons every day. That is so much water. I had no idea. How did he use that much? Pool and sprinklers. And something's probably leaking. I thought, because you know how much I use? I use about 100 gallons a day. And I know because I have to order the water from a company that comes in, they pump in 4,000 gallons. I have to wait for the truck to be there. They have to deliver it, and like it takes like 45 minutes for them to pump it all in. It costs me $160 every time I get 4,000 gallons. If he was spending what I was spending on water, he's going through $80 of water a day. That's crazy. That's crazy. So if you guys have the ability to bug your parents to say, hey, can you tell me how much water we use based off our LADWP bill? Then I'll give you points for every data point that you give me. Up to 5 points. Okay. That's water. Hopefully the tutorial is helpful. If not, you can ask me for questions. Adios, guys.